Foundations of Mathematics for Elementary Teachers. An in-service program designed to provide background for the improvement of instruction in mathematics in the elementary schools. Prepared by E. Glenadine Gibb and Augusta Schurer, members of the Department of Mathematics, State College of Iowa in Cedar Falls. Your instructor, Glenadine Gibb.
A basic concern in problem solving is identifying the relationships inherent in the problem situation, which link the information we know and the information we seek. Today we will consider several problem situations and see in what ways we can link such information. Throughout this series we've made use of symbols. Symbols for number, for operation, for relationships. We have used these symbols to express certain mathematical ideas. Some of the sentences we have used are called open sentences. These are sentences which are neither true nor false, but express a condition which may or may not be satisfied by a suitable replacement. The sentences displayed here are called open sentences. When we replace a variable by an appropriate replacement, we then have what we call a closed sentence. A sentence for which the truth value can be determined. These sentences are closed sentences. The first is false. The other two are true. We use sentences which express conditions in solving problems. These sentences help us to relate the data to the unknown. In elementary school mathematics, use is made of physical situations which reflect the happenings in the everyday life of a child. Children learn to identify in these situations actions associated with addition, subtraction, multiplication, and division. They express the relationships between that which they know and that which they're to find using conditional sentences. Then using their basic knowledge of facts, computation, they find the solution for the sentence which will make it a true statement. This solution then is used in answering the question asked in the problem. Starting from the physical world, they then make use of a mathematical model which relates the information they know to that which they're to find. They find a solution. That solution is then used to answer the question asked in the physical world. Let's consider an illustration of this process. Jane has some cookies in a box. She puts in 5 more. She sees that there are now 11 cookies in the box. How many cookies does she originally have in the box? Let's think about the physical situation. A box with some cookies, 5 cookies to be placed in the box. The action is associated with addition. One set joining the other. The number associated with the first set, we do not know. We can represent that by n. The number associated with the second, 5. We then can write our sentence, n plus 5 is equal to 11. Using a basic fact, we know that the solution is 6. For 6 plus 5 is equal to 11. We cannot check that solution by emptying the contents of the box and separating the set of 11 into 2 parts, one with which we can associate the number 5, the other which we can associate 11 minus 5, or 6. We use the solution then to answer the question asked in our problem. There were originally 6 cookies in the box. Note that the physical situation described leads to a mathematical sentence which expresses a relation between the data and the unknown information. The solution set of the sentence can be identified, in this case, using knowledge of a basic fact. This solution set then makes the conditional statement, a sentence, a true statement, and we use it to answer the question asked in the problem. There's really no set rules for problem solving. Neither is there a neat prescription for teaching problem solving. Insight into problem solving is developed by solving problems. Problem situations can be presented in many ways. To suggest a few, presented in pictures, words, or questions asked of data presented in graphs, charts, and tables. Let's consider a problem presented in pictures. Reading this picture, we see that we have 3 sets of balloons. There are 4 balloons in each set. The action indicates that we want to think of all these balloons together. We can write then that 3 times 4 is equal to some number. Using a basic fact, we know that our replacement is 12. We then can answer the question asked in the problem. There are 12 balloons altogether. But let's consider still another problem. Tom had 8 cars. Harry had 3 wagons. How many more cars does Tom have than Harry has wagons? Let's use these objects to help us think about this problem. The wagons, the cars. How can we express the relationship between what we know and that which we want to find? We can match a wagon for a car, a wagon, a car, a wagon, a car. We see that the action takes place on Tom's set. We have separated that into 2 sets. One with which we associate the number 3. The other which we associate the number 8 minus 3. From that, we can write our sentence. 8 minus 3 is equal to some number. Again, using our basic fact, 8 minus 3 is equal to 5. Our solution, 5, indicates then that we can use this and answer the question. Tom has 5 more cars than Harry has wagons. But let's consider still another problem. Jane has 170 inches of ribbon. She wants to make 21 bookmarks. How long can each be? The physical situation is clear. Thinking of the mathematical situation, we associate that with a line segment. A line segment whose measure in inches is 170. We want to think of separating this line segment into 21 parts equivalent in length. We can determine the measure by thinking of the quotient for the pair 170, 21. We write the sentence 170 divided by 21 will give us what number? The solution that we're looking for. If we perform the division indicated by this sentence then, we would find that our number 8 and 2 21st. We could then say that each ribbon would have a measure of 8 and 2 21st. But suppose that Jane wanted the measure of the ribbon to be a whole number. We do not know then if we can assign a quotient to this pair and have it be a whole number. She would write then her sentence 170 is equal to what number times 21 plus R, which would represent any ribbon that might be left over. Again, she sees that this could be found by division of dividing 170 by 21. Using this process, finding that M would equal 8, R would be equal to 2. She uses a solution then to answer a question. She could have 21 bookmarks, each with a measure of 8, and there would be 2 inches of ribbon left over. But let's consider still another problem. All measurements of a model boat are to be 1/24th of the original measurement. The diameter of the actual porthole is 8/9 foot. What size should the diameter of the porthole be in the model? Again, we can associate with that physical situation the mathematical sentence 1/24th times 8/9 is equal to what number? Using our rules for finding the product of 2 fractional numbers, we then can determine our solution. We find that the solution is expressed by the fraction 8 over 216, or by the basic fraction 1 over 27. The diameter of the porthole on the model then would have a measure in feet of 1/27. Consider still another problem. A football team gains 7 yards on one play. It then loses 9 yards on the next play. What is the total gain or loss of yardage? We associate the physical model here of the mathematical model of a directed segment. A positive 7 associated with one, a negative 9 with the other. We find the sum of these 2 integers. We express then our sentence. A positive 7 plus a negative 9 must equal the n. Continuing then, a positive 7 plus a negative 7 plus a negative 2 is equal to that number. Or, using our associative property and the idea that the number and its additive inverse is 0, 0 plus a negative 2 is equal to n, or n is equal to a negative 2, our solution. How do we use that solution then to answer our question? We would say the net effect of the 2 plays was a loss of 2 yards. But let's consider still another problem. I can buy 2 pieces of candy for 6 cents. You can buy 6 pieces of the same candy for 20 cents. Assuming that there are no discounts for larger purchases, which one of us is getting the better buy? Again, let's use objects to help us think about the problem situation and the relationships between what we know and what we want to find. This represents my purchases, 2 candies for 6 cents. I can see then, for 6 candies, it cost me 18 cents. I get the better buy. But let's record the information here on this table. We see that 2 pieces for 6 cents, 4 pieces for 12 cents, 6 pieces for 18 cents. We have here then, we can think of the pair 2, 6. We can write it in this way. Read 2, 4, 6, or 2 is to 6. The property is also described by 4, 12. Read 4 to 12. By 6, 18. Read 6 to 18. The property common to all the situation indicated in the table is called a ratio. It can be described by any pair of numerals k, 3k, where K is a whole number. The basic pair, 1, 3. 2, 6, 4, 12. Name the same property. We can express this in this way by writing 2 is to 6 as 4 is to 12. We notice that 2 times 12 is equal to 6 times 4, or 24. Also, 618 express that same property. We could write 2 is to 6 as 6 is to 18. We again notice that 2 times 18 is equal to 6 times 6, or 36. Suppose that our pairs were A, B, and C, D. Then we could write A is to B as C is to D if A times D is equal to B times C. Sometimes we express this idea in another way in writing it in this form, that 2 is to 6 as 4 is to 12. This symbolism is the same as we use for fractional numbers. However, here, this does not represent a fractional number. Let's use this idea of ratio in solving a problem. Robert bought a new coat at a 25% discount. He saved $12. What is the original price of the coat? 25%, or 25 per 100, tells us the ratio we need to describe how dollars of discount compare with dollars of original cost. One pair which describes the situation, 25, 100. 50, 200 is another pair, as is 5, 20. But we're looking for a particular pair, one where the first member is 12. We can write 25 is to 100 as 12 is to n. Then 25 times n is equal to 12 times 100. Or we can say then that n is equal to 1200 divided by 25. We now use our division computation to determine what n would be. This will depend on the level of skill. Illustrations of procedures that we might use are given here. But regardless of what procedure used, the solution, 48. We can use then that to then answer the question asked in our problem. The original cost of the coat, $48. There are other kinds of problems which make use of our knowledge of mathematics. Problems in which we have to do some experimentation and assembling of data. One such problem is illustrated by a story told of Karl Gauss, considered by many to be one of our most famous mathematicians. At the age of 10, he and his classmates were given an assignment to find the sum of a good many whole numbers, consecutive whole numbers, say from 1 through 100. Members of the class proceeded much in this way of starting 1 plus 2 plus 3, and after a long process, finally coming in 97 plus 98 plus 99 plus 100. But not Carl. He looked at the situation. He looked at the first number and the last. Their sum, 101. The second number and the second to the last, 101. The third number and the third from the last, 101. He would have 50 such pairs, or the product 50 times 101 would express the sum. He wrote 5050. Another kind of problem is suggested by the numerals that we have here, 1 through 9, and the idea that we wish to arrange these in this one in a cell, whether the sum of the numbers associated with these numerals in each row or each column or each diagonal, 15. We could start out on this by placing a 6 here, a 5, a 4, one sum 15. Or again, we could think of this as 6, 7, and we place a 2, another row, 15. We have here, we could place a 6, 9, but where do we go here to make 15? We'd have to take that out and start again. We could proceed in this trial and error method, but certainly there must be a better approach. Let's think of the sets of numbers, 3 in a set, whose sum is 15. We can list these, 159, 456, and here are the others. We look at this, we see that 5 appears 4 times. 4 appears 3 times. 2 appears 2, as does 6 and 8. This suggests then that 5 must go in the center and that 4, 6, 2, and 8 go on the corners. And so we try again. We place 5 in the center. We can place 4 here. We will place 6 down here. Again, we need to place 2 in a corner as we do 8. Let's put 2 in this corner and 8 here. Now, placing the others, we find that we can place a 9 here, be 15. What should we place here? Our 3, our 1, our 7. We recognize this as being the simplest of our magic squares. There are still other problems, one suggested by this arrangement, where we see these arrangements of objects in squares. We associate with this our square numbers, 1, 4, 9, 16. Can we build, starting with 1, build the next one, so that each time, and then build the one following, so that each time we use all the ones preceding? Let's try it. We start with 1. We then want to build 1, 2 squared, or 4. We join 3 objects to that. We then want to build 1 which has 9 elements. We join 5 more. We continue on, and this time we want to build 1 which has 16. We join 7 more objects. How many will we have to join to build 1 which has 25? We then join again, this time 9. Let's record here what we have done. We started with 1, and that was equal to 1 squared. Then we added to that 1 plus 3, which was equal to 2 squared, or 4. The next time we added 5, 1 plus 3 plus 5, which is equal to 3 squared, or 9. Again, we added next 7, which was equal to 4 squared, or 16. And finally, we added 9, 1 plus 3, plus 5, plus 7, plus 9, which was equal to 5 squared, or 25. What's the sum of the first 100 odd numbers? Or first 10 odd numbers? 100. What's the sum of the first 25 odd numbers? 625. But let's consider still another problem. Think about cutting sandwiches. Sandwiches where you're using a square slice of bread. How many ways can you cut these so that you have two equivalent parts, two parts that are congruent? Most of us would probably think of these ways in which we could cut across on this line. See that we have two parts congruent. Or we think of cutting in this way so that we have, again, two. But are there others? Yes. We could also think of one which would be represented by this cut. If we, along this line, see that we have two congruent parts, or that our parts are congruent. Another might be suggested by a cut in this way. We see again the parts are congruent. Still another is suggested by this. And if we see again, the parts would be congruent. If we would summarize all these cuts onto one slice, it might look like this. We see that every cut passes through the center of the slice. In other words, we could cut this in as many ways so that the line, our cut line, always passed through the center. We would have two sandwiches, which one congruent to the other. But are these the only ways? Consider two other ways that we might think about this. This is suggested by folding the corners here of having two congruent parts. And then we have again thinking of this, congruent to this. We would cut along this line. Again, we would have two parts of our sandwich into halves. Whatever the nature of the problem or the method used in solving the problem, we need to fully understand the entire problem and be able to interpret it. We need to be able to recognize basic laws and formulas which will enable us to relate the data which we know to that which we do not know. Also, in using this, we then can interpret what our computations should be. And of course, it's necessary that we can execute those computations. And finally, having found our solution, we should make a judgment as to whether or not that this satisfies the question asked in the problem. Problem solving that involves comprehension, structure, operation, and judgment.
Foundations of Mathematics for Elementary Teachers has been presented by State College of Iowa under a grant from the National Science Foundation and prepared by E. Glenadine Gibb and Augusta Schurer, assisted by E.W. Hamilton and Diane Baum. The program was produced and directed by Robert Gabler and recorded at KDPS in Des Moines, Iowa.